Thank you very much. Yeah, thanks for the invitation and for this opportunity. It was also for me a great opportunity to talk about the Wiedergutmachung project in its wholity and not just the different components. So please bear with me. This will be a pretty long talk consisting of many different technologies, and I'm very excited to also hear your feedback and if there are any questions afterwards to discuss them with everyone who's here in the room today. And yes, so you already, can everyone now see my screen? Okay, so I will go to the slides. You already talked a little bit about the project that I'm working on. This is called the Wiedergutmachung project. And for this talk today, therefore, I chose the title German National Socialist Injustice on the Semantic Web, from Archival Records to a Knowledge Graph. And I am working on this project at FIZ Karlsruhe at the moment in collaboration with the Karlsruhe Institute for Technology. That's where actually I'm doing my PhD at. And this is a huge project which is being financed by the Bundesministerium der Finanzen, and our collaborative project partners so far have been Landesarchiv Baden-Württemberg and das Bundesarchiv, the Central Archives of Germany, which are important to mention since they've been contributing a lot also for data creation and transcription. And yeah, we are presenting also on the 21st, 22nd of May in Marburg. So yeah, I might see some people over there. I now move on to the outline of what I will be talking about today. So I will start with an introduction of the project Wiedergutmachung. And okay, my slides are being a little bit slow. Yeah. And then I will show you some of these very messy documents that you mentioned, and to familiarize you with the characteristics of this kind of data that we're working with. And then I will move on to this whole digitalization pipeline and in more details talk about the transcription of the documents from scanned images into text files, information extraction from the transcribed documents, and on the other hand of the pipeline, the ontology design, and then the future work, what is yet to be done in order to have the Wiedergutmachung knowledge graph, and also some references to the related work that I've been using during my research in the past few years. Okay, so I suppose most of the people here do know German, so this might be a bit unnecessary, but still I would like to start this with a breakdown of the word Wiedergutmachung and what this means. So the word Wiedergutmachung, that the name of the project comes from, consists of three smaller parts. Wieder meaning again in German, gut is easy, meaning good, and Machung, making. So the word Wiedergutmachung is referring to the act of making it good again for those who were suffering during the rule of National Socialist regime in Germany. And this is, of course, a place of controversy, and whether the term Wiedergutmachung is really the right term to use to refer to this kind of compensation as the best word that we could have or not. That's something to mention at the very beginning, to address this also as a maybe socio-political issue that yet has to be discussed maybe. But anyways, in the context of this project, the Wiedergutmachung is referring to reparations and compensations that were provided by the German government after the end of the Second World War to victims of National Socialist injustice. And this incorporates different groups of people, different individuals, such as people who were persecuted or executed because of their ethnicity, because of their sexual orientation, because of their political ideas and beliefs. And the goal of the project is to eventually create an information system so that there is central, structured, and comprehensive access to all of these relevant documents from the Wiedergutmachung process in an online collection, which is also called Wiedergutmachung for National Socialist Injustice, which is being hosted at the moment at Archival D, which is a subportal of the German Digital Library. So the Wiedergutmachung documents at the moment are spread all across Germany, and it is also interesting to mention that this collection at the moment contains more than, as far as it has been counted, contains more than 100 kilometers of archival records from Germany, and this is only the documents that are here in the different archival institutes within the country. So this shows the scale of the project, and as you can see here, the documents are in different forms. They are on different representation mediums, and I will show some more examples from this 100 kilometer of records later on a bigger screen. As I said, the online collection is at the moment a part of Archival D, which within the Deutsche Digitale Bibliothek. And over this link, you can access the online collection for Wiedergutmachung. And this is an ongoing project. Still, there are some possibilities to look through the records to search for persons under this link. But the project is still not finished, and this will be over the time completed with more information from other archives that are still scanning their documents, and also from other scanned documents that we are still processing and creating the knowledge graph for. So the search options at the moment are still pretty limited, but with the addition of a knowledge graph, it will be a search engine for Wiedergutmachung, and a strong one, we're hoping. And this online collection is providing an overview of all the holdings of the archives, the different archival institutions that the archives can be found at, with more detailed information, such as the date of the creation and the extent of the archives. But also it is possible to find individual records with a record search in this collection. And then the person search is still being developed at the moment. There are some persons that you can find on the person search function of the online collection. And under the person search, you can find some detailed information of individuals, as well as all the records, the index cards, the court proceedings that refer and are related to this person. But also you can find other persons who are related to an individual person. And the goal is to eventually connect these persons to external authority files, to other data sources where this person has been referenced. And that is why we need a knowledge graph for the Wiedergutmachung project. I'm giving you a very small sample of what this knowledge graph will look like. For example, for this card, which is a sample from the Bundeszentralkartei, which I will also introduce later on. This is just an index card that has a summary of an application with the information, basic information of the person who's applying, and the basic information of the person for whom this application is being made. And the goal is to extract the data from such a card and all the other documents from the Wiedergutmachung collection, and create a graph-based data structure in which the different entities are connected. The different entities are connected to their corresponding counterparts in external data sets, such as Arlsen archives, the Wikidata, the GND, and also where it is possible to search exploratorily through this data structure for information that usually cannot be easily searched through a relational database. And the target group that this knowledge graph is trying to reach, the biggest part would consist of relatives of the persecuted people, according to an infographic that has been created based on a survey conducted by the Landesarchiv Baden-Württemberg. They have been observing the people who've been going to the archives to ask for archival records. And the biggest part of this audience consists of the relatives of the persecuted people who want to know about the destiny, about the stories of their loved ones or their acquaintances, but also there are some historians, some general researchers, and some local history researchers who can answer their questions about the process of Wiedergutmachung and post-war Germany based on the information that they can collect, not through single documents, but through the aggregation of the data that is coming from the collections of the documents. And with this motivation, I will show you very briefly this digitalization pipeline as it is at the moment. On one part of the digitalization pipeline, we have the information extraction component, which starts from the digitized archival documents, the scanned documents that we're receiving from the different archives. And at the other part comes the semantic enrichment component, which is resulting in Wiedergutmachung knowledge graph at the end. And through the course of the presentation, I will go through the different parts of this pipeline and explain in more details how the processing of the digitized archival documents is being undertaken in order to create this knowledge graph. But let's start first with the material, the data that we have, the digitized archival documents. So Wiedergutmachung archival documents, as I said, it contains a huge collection of about more than 100 kilometers of records, and they come in all kinds of layouts and forms. They are very difficult documents to read because of the certain characteristics that they have. For example, on the single document, we can see there are already different kinds of text types. There is, for example, typewritten text on a form. And on top of the form, there is also some handwritings, but these handwritings are not very clearly separated from the form, from the machine printed parts. So we have all these overlapping parts where there is an overlap of handwriting text with machine printed text or typewritten text with machine printed text. There are also some documents that are not even scanned, but on microfilm represented. So there are different representation media, and the microfilm documents usually have a considerable amount of salt and pepper noise on them. The layouts, as I said, are very different and not really easily categorizable into certain classes because this process has been going for years, and every institute, every city is using a different form, a different layout for the form. And even on these forms, there are various fonts that are being used in the same form, sometimes even. And there are stamps that are also sometimes overlapping with the other parts of the textual parts of the document and contain important information about the reception of the document, about the institute that is dealing with the document and passing it on to the next step. And all of this information is somehow important for us to extract and to have. Therefore, the loss of information will result in some semantic loss in the whole process. And the documents as they are have been, so at the beginning of the project in 2021, I have to mention this, the documents as they were had been given to some service providers for transcription, and the result of the transcription you can see here on the right. This is on the left you can see an original scanned image, and on the right the raw OCR transcript, and you can see the machine printed parts are quite readable and one can make sense of them, but the handwritten part, which are the information-heavy pieces, which include the data that we're interested in, are truly gibberish. So it is not really possible to work with this kind of transcript as long as the handwritten parts are not read properly. And this is the status of OCR technology at year 2021. It was the case that for a single document which has a mixture of different text types, it doesn't work so well to use the one OCR engine and expect good results out of it. And therefore, our research started with the first research question, which deals with the quality of the transcripts. And we were interested in the techniques and methodologies that we could use to improve the accuracy of text recognition for the archival records, which were historical with the challenging characteristics that I just mentioned. And to address this research question, we found one particular methodology in which the text types on one single document could be separated using a deep learning-based text type separation model. And the result of this would be separated layers based on the type of the text that could be then given as input to respective engines, either OCR or HDR. And each of these text types would be then recognized by a specific text recognition model and then put on top of each other to provide a higher quality document transcript. So that whole process is in the diagram shown on the bottom left part of the information extraction pipeline. And then when we have these document transcripts, we can move forward with extracting information from the higher quality document transcripts. Now, as I showed you before, the traditional OCR engine, again on another sample document, is working well on the machine printed part, but on the handwritten parts of the document, we're not getting any satisfactory result. That was already in 2021. In 2023, transform-based OCR was available as an off-the-shelf solution for working with documents that contain different kinds of text. And it works pretty well, as you can see already on this image. On the right, you can see that the number of the card, which is random digit, has actually been transcribed very well. This shows that the OCR engine is really reading the text, and it's not only based on the language model, which is behind the curtain working, doing its job, but also the number, which is usually more difficult for the OCR engines to transcribe, since there is no correction using the language model because this is random, is also being read correctly. The name of the person is being read correctly. The last name of the person is being read correctly. When it comes to the birth date, again, the numbers is also being read correctly. The birthplace is transcribed well. The marital status as well, and so on and so forth. So this is quite satisfactory. However, these transform-based OCR engines are not always integratable into the digitalization pipeline, especially when it comes to such big-scale projects. There are concerns. In this case, for us, we were using Transcribus. We could not upload our data into their servers because this data is highly sensitive. It is very, we have documents that are still under strict data privacy laws, and it wouldn't be an idea, it wouldn't be a possibility to upload this data with its sensitivity into external servers. To have this service on our own servers, the resources that we needed to allocate were really huge and not possible for our institute. And on the other hand, there's the problem of hallucination and reliability. There were cases where we noticed the document transcript was adding some pieces of text to places where the text did not really belong. And for example, the name of the city where the office of compensation was was being processed as the name of the birthplace of the person. And that's also some error that is being introduced into the model because of the nature of the large language models and the transform-based technologies, which was really undesirable. Therefore, the solution was to separate the text types using pixel level separation techniques. And using this technique for every single document, as I said, you can get classification at the level of the pixels. And using the result of this classification, it's possible to separate the machine printed layer from the handwritten layer of the document, and therefore use the respective OCR, traditional OCR engines, which are requiring fewer resources and usually do not introduce the problem of hallucination. But the problem was that there was no data set that we could use in order to train our own model. There were some publicly available data sets with machine printed and handwritten text, but these are all the IAM database and the CVL database, but these are all based on modern documents with very clear lines and regions in which the handwritten text and the machine printed text are located at, without the noises that we have in our documents, without the faded ink feature, and basically trying out these models that were trained on such documents with which contain both handwritten and machine printed text on our challenging documents was not yielding any good results. Therefore, we came up with a pipeline for creating our own data set by using machine printed parts and handwritten parts of the documents that were already present in the Wiedergutmachung collection. And after annotating these documents with only handwritten text or printed text crops, processing these crops and putting them on top of each other to create labeled crops. So after the separation of the regions that only contain machine printed text or handwritten text, we know the pixels that are darker on these crops contain exactly what type of text. And by putting them on top of each other, we can easily label at the level of the pixel the pixels that are belonging to the machine printed part and the pixels that are belonging to the handwritten part and the pixels that are just in the background. And using this data set, we then trained a fully convolutional network and created a model that was tailored for the archival documents. And then evaluated the model that we had trained using in two different evaluation scenarios. An intrinsic evaluation in which the accuracy of the classification is measured by this metric called IOU, intersection over union, which shows how many of the pixels in the prediction are exactly classified in the same way as they have been seen in the ground truth. And also with an extrinsic evaluation scenario in which we then used the separated layers that were separated using the classification, the outcome of the classification, and created OCR transcripts on the separated layers and measured flexible character accuracy, which is a metric which is working based on edit distance, but regardless of the line order. And you can see here that the baseline model, which was already trained on modern documents, in the intrinsic evaluation scenario was performing with 52% accuracy, but in our different pipelines that we used with binarized and non-binarized crops, this number is going up to 71%. So the intersection of union of the classification task is higher, about 20% in the using the model that has been trained on archival documents. And the mean OCR on the scan documents and the microfilm documents is also going up from 67 and 73 to we have a maximum of 80 and 83. So this shows that the creation of data using our own documents is really helping increase the accuracy of the OCR after separation of the text types, also compared to the baseline model, which was the model that was trained on modern documents. So that is a part that addresses the problem of quality of the document transcripts. But then the following step would use these document transcripts as input, and as output, what we need is structured information. Structured information that will be used then later on to populate an ontology to create the knowledge graph. And in order to get from the document transcripts to the structured information, there are also multiple possibilities. So the first method that we started with was based on regular expression rules. Given the transcripts and given the templates, the patterns that we have on our semi-structured documents, we want to, there are some key value pairs. We are interested only in certain pieces of information. So we want to get the values for these pieces of information, for these keys that we're interested in. Another possibility was to use named entity recognition, since each of these cards contain, I am now talking about the FIZ index cards that I will show briefly. They contain pieces of information that are interesting for us and some words that we are not so much interested in. We don't care if the OCR is working well on those words that we're not interested in. We're just interested in the named entities, on the name of the person, the birth date of the person, the birthplace of the person, so on and so forth. So it is possible to also use named entity recognition models to get this information out of the cards. However, we usually have more than one person on one card, so then that's the problem to deal with. How can we identify which person is this name referring to, the applicant or the victim, the persecuted person? And then there is the other pipeline that is an end-to-end pipeline, which takes as input the digitized archival documents, uses multimodal large language models, and as output provides the structured information. And that is maybe the most interesting part of the talk today, because it's closest to the state of the art of what everyone's doing at the moment. So I'll get to that. I will briefly, however, also introduce the other techniques that we used. But before that, a short introduction to the FIZ index cards. So within the collection of Wiedergutmachung documents, there are about 1.9 million cards, which have basic information on the applicants, on the persecuted persons, and on the proceedings. The information on the proceedings is usually this number that comes on top. That means if you want more information on this particular application, go to this archive and these holdings and use this number to find the archival records that you're interested in. And there you can find more information on the whole proceedings, on the court proceedings, evidence documents, witness documents. And this index card is called the Bundeszentralkartei, the Central Federal Card Index for Compensation. And it contains most of the information on most of the applications for compensation that have been submitted in the Federal Republic of Germany, and they have been kept since 1950s until today, again in different archives. They're all being collected at the moment. That's why right now there is only 1.9 million of these cards that have been digitized, but there could be more coming from different archives again. And the Bundeszentralkartei is the basis for the person search in the online collection of Wiedergutmachung. It is a little bit easier to work with than the court proceedings, since Here we have semi-structured documents. These are always more or less in the same format. There are certain keys that have values. The values are, of course, arbitrary, but the keys are being repeated in all of these forms. However, there are still more than 40 different layout types from different times and from different states that are now being put together. And yeah, the different layout types also sometimes have two persons on them based on the layout type, the applicant and the victim, sometimes just one person. The applicant is the same as the victim. Yeah, okay, so in order to test our information extraction pipeline, we're working with this Bundeszentralkartei. And the first method, as I said, the rule-based information extraction, takes the transcript. So the first step would be text recognition, which transforms these images into text files. The second step would be document classification, to classify the documents based on their layout type. And here we are talking about more than 40 layout types. And of course, there are some outliers as well. And then an analysis of the transcript based on the template and the document layout type using regular expressions. And this means one would need to implement different sets of rules for each of these different layouts or templates, more than 40. And then comes the post-processing step and evaluation. We started doing this with a set of cards from Berlin, Entschädigungsamt Berlin, you can see here, using a Java-based application called Apache Oimaruta, and with the specific syntax of this language, this software, where it is working mostly like regular expressions do. And you can see for every entity that we're interested in, we have to declare the type of the entity and then certain rules how to extract this entity. And here, for example, if the transcript is good, it's very easy to identify the compensation office, since the name of the compensation offices are coming from fixed vocabulary. There are only certain compensation offices. This is unlike the names of the persons or the dates of birth or the dates of death, or in particular the BZK numbers, the numbers that are referring to the archival cards in the Archival Institute, the Archival Records in the Institute. So this was working quite well. You can see over here in an Excel file how the extraction of the information from this set of Berlin cards was working. The green cells are extracted correctly, are pieces of information that are extracted correctly. And the red ones are the ones that are not exact matches. And yeah, so also in terms of numbers on this small set of 38 cards on Berlin, based on per field, you can see here the percentage of exact matches and exact matches plus a Levenstein distance of 1, so partial matches with a small error. And the overall number, we have about 83% exact matches on this one template in our set of transcribed data, and almost 89% when it comes to also partial matches with a tolerance of 1. This is working well. However, 40 different layout types, and yeah, not ideal for cases where the document doesn't actually fit any of these layout types, and those would have to be done manually again. Then the NER-based method, I will just present the pipeline and skip this one, since the limitations are very similar. So this starts also with the text recognition. Then after you have the transcripts, using some NER model to tag the transcript with the named entity labels, document classification on the other hand, so that the named entities can be mapped to the entities based on the templates that they are set on, they're coming from. Some post-processing step and the evaluation. And I just want to mention that for this, we also created our own BZK ground truth transcription data set, and also using two different NER models, FLAIR NER German large, and the ARI NER, which is an NER model which has been fine-tuned on European Holocaust research infrastructure documents. So on domain-specific documents that are coming from the same domain. We use these two NER models on our own BZK transcripts and created also some ground truth to test the performance on a bigger data set. And yeah, I'm not presenting the results. Just wanted to mention that you can find the ground truth NER datasets also in our GitHub repository. The QR code will be there later as well for research purposes. However, these two pipelines have the same limitations, and these limitations are about error propagation. Whenever there is some kind of error in the transcript, this error will be propagated into the step of information extraction from the documents as well. And also from the document classification. So since the attribution and the assignment of the values to the keys is based on the layout of the document and based on the recognized or the predicted layout of each document, whatever error that we have in that step will be leaving its impact also here. And the other limitation is that since these two methods are both based on the templates, they're not generalizable and they're quite laborious, and it would be a laborious task with more than 40 layout types that we have in the BZK index cards. And then also, of course, we are researchers, so we're looking for what's coming next, and the end-to-end information extraction with multimodal large language models seems to be the current way to go. So in this case, we just use an input image and a prompt, then some multimodal LLM. The best one that we have found in our experiment so far is InternVL 2.5. I will introduce this also soon. And then there's an output sequence that can be converted into a CSV file in the format of the key value pairs that we're interested in. And then we have been doing some experiments and evaluating the results of this kind of end-to-end information extraction using the BZK index cards as well. So here I've been talking about the key value pairs. The keys that we have been using for data extraction from BZK cards are the following. We're interested in the compensation office, BZK number, some information, basic information on the applicant, and some basic information on the victim. And that's all the information that's appearing on the index card that we're also interested in. And we have also created a ground truth data set for this kind of transcription or information extraction, which is available on Hugging Face under the name BZK Open. This contains only index cards that are not fitting in the data privacy restrictions. And yeah, so we have a set of 516 cards, which has been split into train, test, validation. And it's very nicely represented on a Parquet card on Hugging Face. You can have a look later. And we've been using this for the experiments with multimodal large language models, which is a bigger set than the smaller template-based sets that we had for the traditional methods. And for these experiments, we've been using we started our experiments with 3 different models. Donut, which is one of the first document understanding transformer models from 2022. Donut is basically a vision transformer encoder put together with a transformer-based decoder, and it's been fine-tuned also on specific data sets and tasks. And the 2 Donut models that we were using, one is Donut-based, the pre-trained model, and Donut-based fine-tuned on Cord version 2, Cord dataset. And then there is InternVL, which is an open source multimodal large language model. There are right now in 2020, and at the end of 2024, InternVL 2.5 was published. Before that, we were only experimenting with InternVL 2.0. They utilize the same architecture. They come in various sizes, however. And then in these different sizes, there are also different LLMs that are being used. So the performance of the smaller size could beat the bigger size based on the LLM that is being used and the use case. That's interesting to know. So we've been experimenting with InternVL 226b, 40b, 76b, and the counterparts with InternVL 2.5, 26b, 38b, and 78b. And in the experiments that I will show later, InternVL 226b and 2.526b, they have been omitted. Also 76 and 78b have been omitted since they were outperformed by InternVL 240b and InternVL 238b in case of our cards. And also to have a comparison with a commercial MLLM, we use GPT-4o Mini, both in the zero-shot setting and with few-shot inference. And in the few-shot inference, we're using static and similar methods for the samples that are being seen. And the only GPT model that we've been experimenting with so far is GPT-4o Mini from 18th of 7th, 2024. And the choice of the InternVL is basically coming from the leaderboard results and diagrams that show that InternVL is on the benchmark massive multimodal understanding, performing sometimes, so in general, overall, even better than the GPT-4o models. So you can see GPT-4o Mini here on this benchmark, which consists of different multimodal understanding tasks, including document question answering and document understanding. And yeah, InternVL 240b and InternVL 2.538b are both standing higher than GPT-4o Mini. But InternVL 2.538b is also outperforming the full GPT-4o model. And since it is also an open source model that we could use internally within our infrastructure, this seemed to be a good choice. Okay, so for the experiments on end-to-end information extraction, they have been using different evaluation metrics, which are quite common in this task: edit distance and normalized edit distance. And these metrics, the lower, the better. The edit distance is the distance between the ground truth and the predicted string, and normalized edit distance is when this distance, which is counted in terms of characters, is normalized by the length of the string that we're looking at. And also accuracy, which is of course the higher the better. And here we've been looking at exact matches with tolerance of 0 and partial matches with a tolerance of 1, tolerance of 3, because sometimes these are tolerable in our use case as well as many other use cases. I think, for example, in terms of the compensation, when it comes to the compensation office is usually a long string, and it is usually in German. So if some characters are mistranscribed, it's not standing in the way of the in a post-processing step, they can easily be corrected. And we are looking at each of these metrics per attribute, so per key, let's say, with an average over all of the images, and also average of the non-empty predictions over all of the images. And this means when there is nothing to extract, has this been also not extracted. And also per image, we are looking at average edit distance, average normalized edit distance, and average non-empty normalized edit distance. And of course, the total average over all of the attributes and all of the images per model, per prompt. And yes, since we're talking about multimodal large language models that work with input images and prompts, I would also like to show you briefly the prompts that have been used. So our basic prompt, number 0, is just asking for provision of information as a Python dictionary. And this Python dictionary is then later converted into a format that we can compare with our ground truth using the keys. So the keys are listed as part of the prompt. We've been doing incremental prompting. I'm skipping some of these, but the checkpoints of these prompts are then in the middle, number 4, in which the terms for applicant, victim, and BZK number have also been specified within the prompt, and some rules for birth years and death years have also been specified. So in prompt 1, we have the terms for applicant, victim, and BZK number in German, and then the rules for birth year and death year that, there are certain years, time windows that these can set in. And in prompt number 9, which is so far the last prompt and the best one, there are also some hints for the birth name with the German term abbreviation GEB, which stands for geboren, and the position of the BZK number, where the BZK number that is referring to the archival record is put and to be seen, and the compensation office clarification. Since some of the stamps are there is this problem of Bayerische Kartei, which is yet another collection and not exactly the name of the compensation office, and this was sometimes being transcribed as the name of the compensation office. So in a negative statement, we clarified that please do not provide this as the name of the compensation office. And there are different experiments and different comparisons over here in this table. Some of them I have selected to show today. Here you can see the performance of 4 different models compared against each other. InternVL 2.0 4TB, just in short 4TB 0, 4TB here. And this model fine-tuned on our own data set, on a small part of our own data set. InternVL 2.5 38B and GPT-4o mini. So GPT model is in blue, the other 3 models are in green, and here you have the number of the prompt 0, prompt 4, prompt 9, and the tolerance for each of these prompts, and then the exact matches. Here I'm including the exact matches with a tolerance of 0, and then the partial matches with tolerance of 1 and tolerance of 3. And you can see that with with all 3 models, except for the fine-tuned one, where there is not much of a difference when the prompt is getting bigger, since the model is already looking at the data that it has been fine-tuned on, and the prompt is quite unimportant. In the other 3 settings, with incremental prompting, the results are getting better. So here from 73 to 74 to 76 in case of exact matches, and same for the other 2 models. And that another interesting finding is that the InternVL 2.5 model is outperforming InternVL 2, but also, even though it's smaller in size, but also the GPT-4o mini. So with prompt number 9, our best model is InternVL 2.5 38B, 83% accuracy. So for over all of the images and over all of the attributes, in 83% of the times, the value is being transcribed correctly, which is to be compared with the rule-based information extraction on our smaller subset of Berlin cards, 38 cards only, which was also about 83% exact matches. But over here we have all the different layouts included, and 1 prompt for all of the different layouts. So it's clearly less human work, more computational power. And with a tolerance of 3, we're getting up to 91%, and this is all before post-processing. So the results are quite good to work with. And in another setting, we also tried zero-shot prompting versus few-shot prompting. And zero-shot prompting, the task instruction is given without any examples, and few-shot prompting, some examples are also given to guide the response. And we experimented with both static and similar methods for few-shot prompting. In the static method, the model is looking at the same example for all of the inputs. And in the similar setting, the model finds the most similar example to what it is seeing in the test set and looks at the transcription of that particular example. So there is a similarity task first. And when the most similar card is found to what we have at hand, what the model has at hand, the model looks at the transcription of that one and tries to learn from that transcription. And this is interesting. This is increasing the performance on some of the keys that we have. I'll show you later. And in these different settings, we experimented with the best model, of course, was InternVL 2.538b, few-shot 1, few-shot static, few-shot 1 similar, and with GPT, few-shot 2 samples for each test card, and few-shot 2 similar. So this means for every test card, the model is looking at the two most similar cards in the train data and trying to make inferences from those two cards. And again, it is interesting to see that the InternVL 2.538b few-shot model with the similar method and only one sample is performing better than the GPT-4 Omni few-shot with the similar method and 2 samples. We have 84% in both cases with a tolerance of 0, but 89 and 92 with for partial matches for the InternVL 2.5 model compared to the GPT model, which is 88 and 91. And more examples are, more experiments are yet to be done to increase the number of samples that the model is seeing. And this needs, as I said again, more computational power, but it would be interesting to see. So this, for example, another finding from our experiments was that in the static model, the prompt is again quite irrelevant. And the performance is not getting any much better with incremental prompting. And this is still ongoing work that I am hoping to publish soon in the conference in SICEM 2025. But yes, so the experiments are already showing some interesting results. And again, to analyze the performance of the multimodal large language model in the different settings per field to see what's going on. Why do we have almost similar results in the pre-trained model and in the zero-shot setting and in the one-shot setting with the 38B model and prompt 9? You can see that in case of the few-shot setting, the BZCon number and the compensation office are being recognized better than the zero-shot setting. But in the zero-shot setting, all the other keys are being transcribed with higher accuracy. These are, again, exact matches, 85% it should be. And this is because in these cases, I think this can be explained by the fact that when the model is looking at the similar samples, the first name, last name, and the birth dates are not really generalizable. The model is not learning from the similar samples anything about the names and the dates, but the model is learning the name of the compensation office, which is being again repeated on the same on the card that it's looking at in the test set. So the name of the compensation office is of course getting transcribed with much better precision in the few-shot setting than in the zero-shot setting, since it's, again, the fixed name that is being repeated again and again. So this is regardless of the performance of the engine on transcribing the text, but rather on being able to learn from what it has seen and to correct itself. And also the BZK number, since there are sometimes patterns when we're talking about one layout type, it is coming from the same archive and it is coming from a particular time. And this means there is some pattern in this BZK number. There are maybe some letters that are repeated in the documents that are coming from the same archive at the same time. And therefore, this element of randomness is less visible here. There is more of a pattern. And in few-shot setting, the model is able to recognize this pattern, performing better, therefore. So the conclusion to this part of the conclusion of this part of the experiments would be that in our case, the best model to use so far has been InternVL 2.538b. And since this is an open source model, I've been trying to include it in presentations also to show to people what they can use, except for the proprietary models. And the best setting so far has proven to be the few-shot one similar with an overall marginal gain. So the gain is not so much, but we still have to experiment with few shots with a higher number of samples to see. And this marginal gain is meaningful for some of the fields. And it can be said that maybe the best of the both worlds is what we want, which is to combine a zero-shot and a few-shot setting to get the best results for all of the fields, and to depend on the different outputs from the different models based on the field. So far about the information extraction. So then after the information extraction is done, we have the structured information, but what to do then with this structured information? And here comes the ontology. So as research question 3, we've been trying to develop an ontology that accurately reflects the hierarchical structure of the archival records, since we're working with different archives and it's important to find the records, and therefore these the findability of the records depends on their position within this hierarchical structure. It is also important that this ontology can reflect the semantic relations, the relationships between different elements within the records, like the damage types, the compensation decisions. So for us, it is important to extract these semantic information pieces and to represent them in our ontology. And also it should reflect the biographical information about the individuals which are involved in this process. And together with the archivists, we've been collecting a set of competency questions. And after the collection of these competency questions, these are some examples of the competency questions, we realized that there are the competency questions can be categorized according to their relevance to which part or which entities we're talking about. Are we talking about the documents? Are we talking about the agents? Are we talking about the process? So, for example, the legal processes are also interesting in this modeling attempt of the Wiedergutmachung process. There are questions about the reparation sums, if they were higher when the victim had a lawyer or not. If there are particular lawyers that frequently appear in the process, and if these lawyers are influencing the legal processing, if there are then some changes in the legal processing with the appearance of different agents within the processes. And therefore, we went for a modular ontology, a modular approach for the ontology design. And the core concepts of this ontology will then consist of archival documents and their hierarchical structure. The agents include also institutions and persons and their relationships with one another, and also their biographical information, both for biographical research and for prosopographical and historical research. And then also the legal processes are interesting for us. So the ontology, I'm not going into very much detail, but I would like to mention the ontologies that we've been reusing for each of these modules. So for reflection of the archival hierarchy and the interconnections between the archival records and the archival holdings, we found RICO to be the best ontology to use. RICO is the Records in Context ontology. It is currently being maintained. And it has this property that you can use. There is a class record. And this class record can have multiple subclasses, and in this case, we are defining our own classes for each of these subclasses based on the record type. And the record is itself a constituent of a record set. And you can define a record set or a record as you it fits your use case. And also it includes record part, RICO in its classes as one of its classes. It goes from record set to record and then to record part. And this record part is also interesting for us since we have also stamps that include information. So for provenance information, it's really nice to have the granularity that RICO is offering. And then when it comes to the legal processes, we've been looking into reusing Provo, which is an event-centric ontology, which connects activities or events to agents to entities. And in case of Wiedergutmachung, we have as activity the different parts of the process of Wiedergutmachung, which is the application, the investigation by the court, the decision-making. In case the applicant is not ready, is not happy with the decision-making, then this whole process can repeat again through a complaint, which itself can be an activity. And there are different entities that are the documents that are informing each of these activities, and there are different agents that are associated with these documents or these entities. So the circular property of Provo and its event-centric nature is very fitting to the nature of legal processes, and therefore we've been going for Provo in this case. Cydoc CRM for agents, since this is the mostly used namespace for the representation of persons and agents within the field of cultural heritage. And then our own ontology, we're naming it Court Docs. This is also a work in progress. We have the data model and the specifications and the requirements for the data model. However, the ontology is not existing yet. And yes, there are then class-specific, some domain-specific classes that we're defining, such as the damage, for example, and the different types of damage that people can apply for compensation for. Yeah, okay. So then when the ontology is there and the structured information is there, together with the metadata and the vocabularies that are coming from the archives after some post-processing and the creation of the RDF statements, can altogether be mixed and construct the Wiedergutmachung knowledge graph. And on the other hand, the last part of my work on this project would contain a research question 4, which is about linking of the entities to external sources. So there are different databases such as Yad Vashem database, which are domain specific, and then there are also the general authority files like the GND, gemeinsam-Datei, or the Wikidata that our entities will eventually be linked to. And yeah, so the question would be, how can we establish reliable links to disambiguate these entities that we have extracted from digitized archival records and connect them to external databases and authority files? And this would be then part of the future work and takes me to the rest of the future work, that is to be done in the coming year or two. Information extraction from the semi-structured documents. We're going to conduct further experiments in the few-shot setting and with maybe also some other GPT models to not be limited to GPT-4 mini, maybe DeepSeek, yeah. So there are new models coming out every day. Full-fledged comparison of the 3 different methodologies, the NER-based one, the rule-based one, and the MLLM-based one, to see if in terms of performance, one is, in terms of precision and recall, one is preferable to another one. So there are different comparisons that can be done. And for the ontology development task, the biographical module is yet to be designed, and the ontology has to be created. And then the research question 4, entity disambiguation and entity linking, to map the extracted information to unique entities. This is an idea to use GND4C toolbox, which is an available toolbox that also some of our colleagues at FIZ Karlsruhe have been working on, to connect persons to GND. So that will maybe would be one possible direction to go into. And then, yes, connecting the knowledge graph to external sources is also part of this research question. Eventually, there will be there should be a competency question-based evaluation of each of these pipelines versus the hybrid pipeline, where we take the best results from each of the, where we combine the best results for each of the specific fields, for example, according to the model that is performing the best on that particular field. And yeah, with this, I will just guide you to the references. I hope the slides will be also made available later. And here you can find some of the models, some of the papers we've been using, and more details about each parts of this pipeline. You can find, of course, in my own papers as well. And I would also I would like to share the QR code to the GitHub repository, where a lot of this scripts, a lot of the images and data sets that I've been working on and creating are available, and the Hugging Face card for the FIZ open data set for information extraction. And yes, thank you very much for your attention. I hope there's still some time for questions.